So just a quick note, I realized on reviewing the last piece of footage that there was a point where I said out loud 27, but I meant to say 21. I wrote down 21, I did the right calculation with 21. I'm way too lazy to edit it and make myself say the right thing, so I'm just going to move on because it doesn't matter. Problem 4. Recall that the Fibonacci numbers are defined inductively in the fashion you see on the screen before you. Well, now let's prove that for any n, the statement you see on the screen in front of you is true. Well, because the Fibonacci numbers are defined inductively, it seems like a good idea to use inductive proof. It's in fact a great idea. It's the idea I will follow. So, think way back to the beginning of this video, or the discussion section, or whenever, when we saw that the GCD of A and B is the same as the GCD of B and A minus B. Again, why is that? Well, a common factor of A and B must also be a factor of A minus B, and conversely, a common factor of B and A minus B must also be a common factor of A and B. It must also be a factor of A. Since they have the same common factors, AB and BA minus B, they must have the same greatest common factor. That proves this fact. Alright, it underlies the original Euclidean algorithm, but that's not important. It doesn't matter about the algorithm. What matters is the fact. And we're going to use this fact in our inductive proof. So, the base case is easy enough. I don't even need to bother you with the base case. Or maybe I do need to. Maybe they'll yell at me if I don't cover it. So let's note that if n is 0, the lowest natural number there is, we have that this fact is true. Base case. GCD of f of 3 plus f of 1, comma, f of 2 plus f of 0. Well, that's the GCD of the third Fibonacci number. Let me figure this out. Okay, x, f of x, 0, 1, 2, 3. All right, 0, 1, 1, 2. Great. Third Fibonacci number here is 2. First Fibonacci number is 1. Second Fibonacci number is 1. 0th Fibonacci number, which is really what we mean by first, I suppose, but never mind that. 0th Fibonacci number is 0. Maybe instead of first I should have said 1th. Doesn't matter. GCD of 2 plus 1 and 1 plus 0. That's the GCD of 3 and 1. That is 1. The only thing that divides 1 is 1, or negative 1 if you include negatives. So the greatest common factor of anything in 1 is 1. That's our base case. Now let's move on to the inductive step. Alright, the base case is taken care of. The screen has finally been resized properly, at least on my end properly, and I even changed the x at the top to look less like a lambda. Everything is coming up roses. Now let's tackle the inductive step. Assuming the fact at the top holds true for n, the way it's written at the top. F of n plus 3 plus f of n plus 1. I realize the parentheses are vital to the meaning here, but I'm not going to say them out loud. I'm just going to write them down. And f of n plus 2 plus f of n are relatively prime. That is, their GCD is 1. Given that starting point, can we show the same fact when we replace n throughout by n plus 1? Well, the GCD we want to calculate, f of n plus 4 plus f of n plus 2, with all the parentheses in the right place, comma, f of n plus 3 plus f of n plus 1. Oh, my f's look like pluses. Fixing my handwriting is probably a lost cause. By the fact at the top of the page here, calling this first argument A and this second argument B. This is exactly the same as the GCD of that second argument, f of n plus 3 plus f of n plus 1. And note how nicely this lines up with the fact we're given as an assumption, comma, the first argument minus the second argument, f of n plus 4 plus f of n plus 2 minus f of n plus 3 minus f of n plus 1. And by the inductive definition of the Fibonacci sequence, f of n plus 4 minus f of n plus 3 is f of n plus 2. Since each item is just the sum of the previous two items, the n plus 4th item is the sum of the n plus 3rd item and the n plus 2th item. And f of n plus 2 minus f of n plus 1 is f of n in precisely the same way. And so we see that the GCD we have to show is equal to 1 is equal to the GCD we're given is equal to 1. And so we're done. QED.